All right, we are in 5.2, and we are evaluating and also graphing polynomial functions. Um, Polynomial functions are like monomial functions or sum of monomials, and if you were to generalize what a polynomial function is, it could be represented as f of x, which is a function of x, equals a sub n, which is considered our lead coefficient, times x to some n power, whatever the largest n power is, plus um, whatever coefficient is attached to x to the n minus 1, and so on, all the way up to where we have a sub 0, which is our constant. So constant means it's a number that has no variables attached to it. If you were to graph a constant, it would be almost like a horizontal line, and it would cross at wherever the y coordinate touches. So say if it was like 5, it would intersect where y is 5. So some of this is a little bit of a review. So if you were to look at some of these are the more common polynomial functions. Like I said, the constant, where it's f of x equals a sub 0. And this could be like I said, f of x equals 5, which would be like, if you were to graph it, would be a horizontal line. Linear function is where you just have x to the first power is our degree, and those are represented as a linear function, which is a straight line, where you'd see like f of x equals 2x plus 5, where our y-intercept would be 5, our slope would be 2 over 1. We have quadratics, which is where our large exponent is a square unit, and then you can write it as f of x equals x squared plus 5x minus 13, something to that extent, and it keeps going on and on. So one of the things that we're trying to look for is we want to identify polynomial functions. And to tell whether or not they are or are not polynomial functions, there are two things that we have to keep in mind. First, we have to see if any exponents is negative. If there are any negative exponents, then we can conclude that it is not a polynomial function. Another thing is if we have a variable as a exponent, we can then conclude that it is not a polynomial function. So what they want us to do here is, if it is one, write it in standard form, find its degree, and then find the leading coefficient. So if I look at A, I have g of x equals x squared minus 3x to the fourth plus 1/2 x minus 7. So has no negative exponents. It has no variables as an exponent, so I can say that this holds true. So if I was to write this in standard form, my largest degree is to the fourth power, so that's what I'm going to start with. So I'm going to have negative x to the fourth. Next would be squared, so I got plus x squared plus 1/2 x minus 7. So that is how it would be written in standard form. Again, my degree would be 4. My type would be like a quartic function, and the leading coefficient would be -3. So for B, I look at it, I see that I have a variable as my exponent. And since it has a variable as an exponent, I can say this is not a polynomial function. I look at example C, f of x equals the negative square root of 2, x to the second plus pi. That has, this has positive exponents. It has no variables in the exponents, so I can say that yes, this is a polynomial function. It has no, this is actually written in standard form, so this is a quadratic. The degree is 2, and the leading coefficient is a negative square root of 2. Okay? For D, I have f of x equals 3x to the negative third plus 2x plus 7. I notice that it has a negative exponent, so this is not a polynomial function. When you're evaluating polynomials, you can do it doing it two different ways. One of which is very familiar to you, the evaluating using direct substitution, and then also you could use synthetic division. We're going to ask you to use both. So for example A, I have h of x equals 3x cubed minus 5x squared plus 15, and they want x to equal 3. So when I use direct substitution, all I'm doing is substituting in my 3 and for the x spots in our function. So this ends up equaling 3 cubed minus 5, 3 squared plus 15. Using, order of operation, 3 to the third power is 27. 27 minus 3 is 81. And then I have minus 3 squared is 9. 9 times 5, that makes it 45. And then I have a plus 15. Do the correct adding and subtracting in here. This comes out as 51. Okay. Second example B, I'm going to substitute x in as negative 2. So I got 9, negative 2 to the fourth, plus 3, negative 2 to the third, minus 4. So use my order of operations. I'm going to take care of my exponents. So I got 9 times, this will be a positive 16, plus 3 times a negative 8 minus 4. We're going to do multiplication, so that's 144. So that's what, plus a negative 24 minus 4. And this ends up being 116. Okay, so that's how we were to solve using direct substitution. Another way is what is called synthetic division. You're going to get the same answer, so I'm going to show you using the example in A. So what I did is first you're going to make like a half of a box, kind of something similar to this. Then you're going to attach on the left-hand side here, you're going to put what you wanted x to equal. So then inside of this box on the top, you're going to write down the leading coefficients of each of the values in each variable. Now, if it doesn't give you one of our variables to some power, I want you to write 0 as the coefficient. So here in example A, I got x cubed is my leading degree, so my leading coefficient is 3. Then I have negative 5, which is my squared. I don't have an x, so I have to write that as 0, and then my constant can be written as 15. Now, first thing I'm going to do is I'm going to drop down that 3 here, Then I'm going to take 3 times 3, so I'm multiplying these two together, and that gives me 9, so I'm going to write that here. Now I'm going to add these two numbers together. This happens to make it 4. Again, I'm going to take 4 and multiply it by 3, which gives me 12. And adding them together gives it 12 here. And then 12 times 3 gives me 36. 36 plus 15 gives me 51. Same answer as I had when I used direct substitution. Okay? So let's do some other examples. I have example A here. They want to use synthetic division. So I have g of x equals 4x to the fourth minus 3x squared plus 5x plus 7. X equals -1. It's in standard form. We're good at this point. So I'm going to make my little half box here. So I have -1. And leading coefficient here will be 4. I don't have an x to the third, so I'm just going to write 0 in as my coefficient. Then I got -3. I have 5, and then I have 7. So first off, I'm going to take that 4 and drop her down. Then I have -1 times by 4, so that gives me -4. Adding those together gives me -4. Multiply -4 times -1 gives me +4. -3 plus 4 is 1. 1 times -1 is -1. 4 times -1 is 4. 3 times -1 is -4. And 7 plus a -4 gives me 3. So my value for when g is -1 ends up equaling 3. So let's look at B. So I have x equaling -4, where 7x to the third plus 5. So I got 7 as my leading coefficient. I don't have an x squared, so I write that as 0. I don't have even an x, so I have to write that as 0. And my constant is 5. So drop down at 7. So now that gives, multiply that by the -4, it gives me -28. Drop that down, I got -28. Multiply -28 by -4, that's 112. Add those together, so that's just 112. Multiply 112 by -4, that is a -448. Add that to 5, that gives me a -443. Okay? Here's the portion where we're going to talk about graphing polynomial functions. And when we're dealing with our x values, usually that's what we're talking about when we're going left to right or right to left, whatever that may be. And if we're going to the right-hand side of our graph, that means that x is going to be positive. And if we keep going to the right, that means that x is becoming really, really, really large. So that means that it's going to approach what is called positive infinity. If we're going to go to the left-hand side, which means is that x is becoming a very, very, very small number, a negative number, and or a very large negative number, I guess is the better word for it. So that would mean that x is approaching negative infinity. And if f of x or y, we're going up or down, if we're going up, that means that we're approaching positive infinity. If we're looks like we're going down, it means we're approaching negative infinity. So looking at end behavior is what our f of x or our y is doing with respect to x as it's going towards positive or negative infinity. Okay? So if I look at this first graph, I have to identify it as, well, we're just going to generalize it. So let's just say that if we have a function whose leading degree is odd. So like say I have it as x to the third power. 3 is an odd number. And the coefficient of this is positive. So like say I have 3x to the third power. It may look something kind of like this. And the reason why is because it's the third power, because it has the possibility of crossing the x-axis 3 times. We got 1 here, 2, and 3. That's where the exponent comes from for that. So, but what we're going to do, what we're going to explain here is if x approaches negative infinity, which, so that means in our x coordinate here, it's going this way and it's becoming very, 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 very large in a negative aspect. So as x becomes going towards negative infinity, our function f of x or y is going downward. So that is going to be approaching negative infinity. Looking at x in a positive infinity, as you can see, as it's going towards the right, our f of x or y is also going towards positive infinity. Okay. Now we're going to still stay with an odd degree, but what we're now going to do is we're going to look at if our lead coefficient is negative. So it kind of looks something kind of like this. You know, here I have 1, 2, 3. This could be a, like, say, negative 5x to the third power, so to speak. So as I look at x here, let's say if I'm going towards the right in a positive infinity, as x becomes large going this way, I can see that my f of x or my y is heading towards negative infinity. So it's becoming much smaller. Looking at x as it's approaching negative infinity, so that means it's our x value is going towards the right. That means that as it's going towards the going towards the left, my apologies, our f of x is pointing upwards. So if it's pointing upwards, that means that as x approaches negative infinity, our f of x is going to be at positive infinity. Okay? Now let's take a look at it, say if our degree was even and our leading coefficient was positive. So it would look something kind of like this. This is kind of an example of a quadratic. Many of you guys have seen this before in other classes. We've had to graph these kind of functions. So what I'm looking for is if x is going towards negative infinity, I can tell that my f of x is still going large and it's still going towards positive infinity. If my x is going towards positive infinity, my f of x or my y is also still going towards positive infinity. Looking at an even degree with the leading coefficient being negative, if my f of x is approaching negative infinity, my f of x or my y is also approaching negative infinity. And if my x is approaching positive infinity, my f of x here is still going towards negative infinity. Okay? So what I was looking for in these examples is I wanted to know or be able to describe the graph determining its end behavior and then completing the statement. So this is like almost like I want you to complete this statement for both if x is approaching negative infinity and also positive infinity. I want to know what f of x is doing when x is doing those two things. So for f of x equaling 9x cubed plus 2x squared minus 5, I know that my degree is odd and my leading coefficient is positive. So as x is approaching positive infinity, my f of x here is also approaching positive infinity. If my x is approaching negative infinity, my f of x is approaching negative infinity. So that's what I mean by completing the statement. For C, g of x equals negative 5x to the 6th plus 10. So I know that my degree is even, and my position or my leading coefficient is negative. So with that, I know that as x approaches positive infinity, then my f of x is approaching negative infinity. If my x is approaching negative infinity, my f of x is still approaching negative infinity. Last thing that we want to do is we're going to graph these polynomials. Describing the behavior is important, but many times we can make conclusions of those behaviors by making a t-chart and plot points. So what I want you to do is I want to give you a standard values for x and y. Standard values for x. I want you to plot like -3, -2, -1, 0, 1, 2, and 3. And we can use direct substitution for these values of x and plug them in and then we get a y, or this is also f of x in functional terms. So if I were to say if x is -3, my y or my f of x would be -55. If it was -2, it'd be -17, -1, -3, 0, -1, 1 and 1, 2 and 15, 3 and 53. Not all of these points can be plotted on this graph. I don't have enough room, but I can plot some of them. So I can plot -1 and 3. I can plot 0 and -1. I can also plot 1 and 1. And as we look, it has my leading coefficient is 2, so it's positive, and my degree is 3, so that means it's odd. So is my x goes towards negative infinity, my f of x goes towards negative infinity as well. That shows that as my x is getting smaller, so is my y or f of x. And, concluding that as my x is getting larger towards positive infinity, so is my y. And so if I were to kind of sketch this, this kind of look like something like this. It doesn't have to be exact, it's just a sketch. Okay. And for E, I have g of x equaling x to the 4th minus 4. So I'm just going to, I want the standard -3, -2, -1, 0, 1, 2, and 3. And I'm going to plot these points. So if I have it's -3, my y or my f of x equals 77, negative 2 gives me 12, negative 1 gives me negative 3, 0 is negative 4, 1 is negative 3, 2 is 12, and then 3 is 77. So again, I can't plot all these points, but I can plot some of them. So I can go negative 1, negative 3, I got 0 and 4, and I also have 1 and negative 3. And if you look as my x approaches negative infinity, my y or my f of x approaches positive infinity. And if as my x's become extremely large going towards positive infinity, so does my y or my f of x. So if I were to kind of sketch this, it's kind of like something kind of like this. Okay? And that is being able to evaluate polynomials and graph polynomial functions. Hope this helps. Until next time.